All right, let's check this out. So we're gonna look at some implications of this quantum gravity idea that I happened to come across. And the reason I came across it was because I was kind of trying to prove the Riemann hypothesis was correct, right? So I was like, all right, let's prove that no matter what you do, that line is gonna stay straight, right? It's always like you can give it whatever kind of slope you want. You can keep like messing with it, doing all kinds of transformations and stuff, but um, unfortunately, I found a way to curve it, and I was like, dang, okay, that's kind of weird because it would give some very strange implications for reality, essentially. It would have some strange implications. So let's see if we take that critical strip and we start to take infinite linear transformations. So we just linear transformation. What we're taking is these zeros, and then we're projecting it onto basically a different axis here. Okay, and so when we do that again, and then again, and we just do this, we just get straight lines all the way down, so we get new sets of zeros every single time, which is fine. That means that time should theoretically go on forever, right? Okay, because that's the implication of being able to take infinite linear transformations is that time uh, would essentially continue forever, because each transformation is pulling up a new dimension out of thin air. So whatever. If we go to the left over here, we can do is we can take nonlinear transformations. We can take logarithmic transformations, and you can't really see the curvature here of the line because it's very subtle. But what's happening is that these numbers are actually going down to basically zero. Um, they're all going down to the same zero over here. They're becoming really, really small, and those are kind of like one right now. But essentially, if you kept doing this forever, you get to the same zero. Um, so that way, all the zeros converge to no unique zeros. And this essentially could represent the beginning of time because everything would just be 1, 0 there. And the moment that you undo this process and you start undoing those logarithmic transformations, what do you get? You get exponential growth. So you're actually going to get exponential inflation doing it this way. So this is essentially this direction. This direction takes you down to like the beginning, and it does so in a logarithmic way. But going this way gives you an exponential inflation of the zeros. And so therefore you get this crazy thing that's happening, which seems to be inflation. All right, well, that's interesting. So then if you take exponential transformations and you apply that, what essentially happens is that going this way, you start reaching infinity, or say all the zeros will become the same infinity. Something like that. You see what I mean? But this way was exponential, so what I'm saying here is that this is an exponential direction this way, and this takes us to infinities, or rather singularities, say black holes. Yeah, so I guess I already wrote the word singularities there, so I'll just put black holes here. Just so much mass down there. It's just like, what the heck? And if you undid this, obviously, there would be a certain point where you could reach this level here, which would essentially be the event horizon, where all of a sudden the curvature isn't so strong, so you don't have like too much stuff pulling you. Look at the curvature of this line; it's like sucking you down really fast. So and that's essentially a point where the curvature will stop being so sharp, and that's where we would find the event horizon, not so sharp. Curvature is not so strong. Well, it's definitely strong, but it's just critical. This is the critical point where you can't really go past or forward, so that's kind of that. And then, of course, you escape that, you're back into the linear zone where you're continuously just taking linear transformations until the end of time, unless you, unfortunately, you're kind of following the straight line down in a sense. You're following the real timeline of zeros, because obviously there's an imaginary timeline, but there's also a real timeline, a real line of these zeros. So, I don't know what's happening with my computer, but sometimes it likes to break. So I'm just going to close this and reopen it. Okay. So, we have that. And here we're all just floating in the vacuum of space. Everything's fine. We're just going on time forever. Unless, yeah, we just come across one of these little curved lines that just take us down to the singularity. Wouldn't be very good. But these are sort of the implications, the beginning implications that I was starting to notice about curving the Riemann function. Because I was like, I don't think this is true. I don't think this is true. I think this is kind of nonsense. I think the hypothesis is true, right? Well, like, I found a way to curve it, and then all of a sudden, these things, these ideas popped out that sort of, it was an implication. So I said, all right, let's just run with it. Let's just say, let's just say that's true. Well, now, okay, then we have another problem we have to do. So we have to set up some axes. So I wanted to make sure that the axes could represent space-time properly without messing anything up. Because the key is that we can't change anything in terms of like what's already here. All the real physics is real. Like I'm not changing anything. I'm not changing anything. I'm just looking at how quantum mechanics influences gravity and how gravity influences quantum mechanics. And of course, their strengths are so and gravitation is so weak, quantum mechanics is essentially can ignore gravity. So you want to leave them untouched is essentially what's we need to do. So let's count some axes. Um, so if we have this zero, this is a real zero, and then we have another real zero over here. We have two real zeros. Let's represent this type of pairing here as, well, they both have basically an alpha. If we consider an imaginary zero to have let's see, an imaginary zero. Get this one. Imaginary zero is going to have not only the alpha, but he's also going to have beta I, or I beta. Whatever, it doesn't matter. We'll just keep the I right here. And really, this is the I that's more important. So it has this complex component. And if we pair these guys together, then we get something that's like this. If we pair these together, then we get something that's like this. Um, and this is purely real right here. But what if we paired these two together and we get something else? Like, oh, I screwed that one up. Okay, we gotta just copy this and then copy this. So that way we can get the pairings here. And, well, if we wanted to multiply some matrices together, then we would have trouble multiplying this type of matrix with this type of matrix. Okay? That's kind of going to give us a little bit of trouble. So you can't just like multiply this by that. It's going to take a little bit of time to visualize and sort of understand. There is one way that these things interact with, but you'll notice that there's differences between them. And if we set this up as another matrix over here, we can see how this one. So the ideal pairing is going to be another matrix of its kind. So these things work really well together. These things work really well together. These things work really well together. And you know, uh, these have bits of this, and these have bits of that. And what's interesting, you'll notice, all of them have alpha. So I'm going to highlight that because it's pretty important. The fact that every single piece of this has an alpha shows you that they're all linked through the real components, but yet they can't interact except through that linkage, in the sense that they have the same real component. This is freaking insane, but yeah, this is crazy. So this alpha stuff essentially carries this stuff carries curvature info from how these things are twisted together in the background, because obviously these zeros are somehow linked, and these ones are linked to those, but these are linked to those and linked in other ways. So they all kind of have this link between them in the background. But of course, in the foreground, you can see how they can't interact except through that linkage back there. And so they have this curvature information sort of behind them. Um, so this little guy here is the Higgs. He's the real zero, right? Isn't that all that is just a real zero, just one of those. So all we've done is basically find the Higgs boson right here. This has a spin 0. Now, what does that mean, spin 0? It means that if you look at the 0, no matter what direction you look at this alpha, it's always going to be an alpha. There's no way that this alpha is going to change. It has no rotational component. Look at this one. This alpha has a rotational component. You could change this particular alpha um, with this 0 right here. It can be changed through this transformation. We can transform those zeros using e to the I theta if we wanted to, which would give us a spin 1. So let me just give this thing over here because this is all the ability of an imaginary 0 is to spin out. That's the ability that imaginary 0 has. Now, the normal 0 can't spin out, so it's not gonna, every time you look at it, it's gonna be that Higgs. But the imaginary zeros can spin out at two different ways. They can do this with a full spin or a half spin. So for some reason, they've decided that dividing by 2 is okay. And kind of those are the only things. And I have an idea for this. The idea that this comes from this fact that we only have one zone here, one axis that the real components can work with. This gives us the ability to go up to one spin, up to one, up one spin is possible with this. Uh, Over here, we have an additional, this thing here, this can contribute half spins. It can contribute, possibly might contribute 3/4 spins. But the reason we don't have 3/4 spins is because we're only allowed to get one spin in total here. Like this is some possibilities of why we only see one spin. And then over here, we kind of have this thing that's gives us two spins. Because now we have this and that. Spin 2. This is theoretically the graviton. I mean, well, Actually, it's very important that we have this. This is essential that we have this little thing. I don't know what we're going to call it, but I'm just going to go ahead and label it the graviton. If you don't like that word, we're going to call it dark matter. And this is critical for the emergence. Well, it's critical for the universe. We know that this is definitely important for the creation of the universe. It's also important for this theory to function. So, the fact that we have this here is pretty important. And it's going to do some stuff later that we really need it to do if we want it to act like dark matter. And in fact, these things like dark matter. And these things act like the bosons and the fermions and stuff. So these things act like bosons, and these things act like fermions. Okay, if we happen to measure something here, it's not. I know seems a little bit crazy, but yeah. So this is the spin one, and this is the spin 1/2, and we've designed that. Well, the real world can interact with up to one spin because we have this one real axis. Um, but the Higgs is spin 0. We've already determined that over here. So that's fine. But anyway, here we can get spins of 1/2, spins of 1. These ones can spit out gravitons with a spin 2. It's exactly what they want, right? For some reason, we've determined it's spin 2, and it would make sense according to this theory. Um, it's quite possible that in this imaginary realm over here, because we have a spin 2, because we have two axes here, we might be able to get the spin of 3 over 2. So that's kind of a possibility. We don't really know the nature of dark matter that much. So the question of whether we have 3/4 spins is still a one, I don't know. It's more like a question mark here. But the spin 2 graviton could potentially be dark matter. There's a whole bunch of things. They could also have more of these things that work with it. But I think we actually have already detected these. So I don't think we're really going to detect any more. I don't think this is probably not going to be the case. Maybe, I mean, we don't know how many dark matter particles there are. Could be like that. But it's really hard to interact with pure imaginaries. Yeah, really hard for, this is all we got right here. And then we can barely reach into this dimension right here. Look at that. We can barely reach and touch these things and see what they're doing because they're doing stuff. But it would be really, really hard for us to interact with all this except through that curvature right here. So that's how we can sort of detect these things so far. Okay, so that's kind of that. And now we have sort of shows us how all the zeros give us all the particles. And we want to take a look at how these zeros might connect in terms of like creating planets and stuff because the idea is we have this linkage of real zeros that are gravity. No, no, these are the Higgs really. These are the sort of the things that are holding things, but real zero, real timelines lead into this like that. These are of course going to be curved inwards. It's like gravity. Yeah, so you have to follow these lines, and of course these lines are going to have zeros along them. Awesome. All real zeros here. Okay, it's all real. Yeah. You get equipotential zones over here. It's fine. Yeah. But this is essentially how gravity works. Right? and the curvature gets a little too intense, you know what happens. In the meantime, uh, we have uh, we have imaginary zeros as well connecting, right? So we kind of have these things helping them out too. But the cool thing is imaginary zeros can do a lot of cool things. So like they actually have this extra axis that they do. Let's try to connect these things. These are gonna be like this, something like this. Um, there's gonna be like a pole right here. I can do this correctly. Let me make that up. I think I'm seeing it here actually. Something like this, where it's gonna lead into the imaginary sort of realm through this particular connection. And it's like seaming together how these zeros can actually interact into our world. So yeah, that's kind of basically the electric field lines forming around uh, planet Earth. I think it's just like a magnetic field. I don't know what it is, but the idea is that there's a field. There's the magnetic field or the EM field. I have to look that up, but there we know there's a field there that does this. And then we have an equation for it too. Just gonna put that out there. So just gonna throw the equation F or theta secret partial of this A thing that we're gonna take a look at later. And the radius. This is a field here, electromagnetic field, and then minus dAr over d theta. And this governs the electromagnetic field, well, one of them. I think the other one is governed by the phi version. One of them is the magnetic, one of them is the electric. So let's just put both of them. So now we change this to the phi. It's right here. Awesome. So yeah, so we're able to interact with this partially. It gives us things like photons. There are other ways. We have things like electrons and protons and neutrons. So, but the EM field is mainly just a photon field. So we'll just leave it at that for now. You see the electric field here. I swear to God, I think the electrons and the protons also do stuff because these things are positively and negatively charged. So yeah, exactly. That's kind of where we have to deal with the spin of 1.5. They can also interact with this stuff as well. So this is the 1.5, and this is the one. So that's kind of cool. Now let's also note the fact that these things, as you continue outwards here, these particular lines actually become quite thin. And it would make sense because we're following the imaginary zeros on these are imaginary zeta zeros in the critical strip. That the distance between them gets smaller and smaller as you go further out. So keep that in mind. The distances get very, very small and essentially dissipate. So that is what happens there. And we know that as we go further out, the magnitude of this electric field decreases with the radius. So as we continue to extend this radius going to infinity, well, let's just say this, the radius is increasing, the electric power, the E field, will in fact decrease, as shown by the sort of distances between the zeros. All right, and the distances between zeros decreases. All right, whatever. It's kind of like weird, but this basically implies that the distances decrease and therefore the electric field is. This is the reasoning. The radius increases, therefore the distances decrease, therefore the electric field decreases. That's that particular logic there. Uh, this is a result of the spacings decreasing, in fact. So when we have that happening, um, yes, the dark matter formations. So far, we can see how the imaginary field is pretty important to us. It's giving us some powers. It's giving us some ability to sort of model some stuff in our world. What about these imaginary zeros? What are they going to do for us? Why do we care about the imaginary zeros? The imaginary zeros are interesting. They're going to do very much the same things, but at the same time, they're also going to be doing all sorts of other things. They're going to be going haywire because these things have distances decreasing between them. The real zeros don't. Therefore, the real zeros kind of behave pretty nicely. Look at that. Look at all that. They can connect to these ones, and so we can get some info from there. Uh, but so now we're dealing with dark matter. So these things, the dark matter, these are pure imaginary zeros. I will go ahead and should I just darken this or something? Let me try to find a better color. It's kind of like here in the middle. And we're gonna put those zeros. Still not quite dark enough. Oh, it didn't change the color. Okay, there we go. So yeah, so now these real zeros, they could be all sorts of places, wherever they want to be. They're gonna be there. They're gonna be here. They're gonna be here. You're gonna find some over here. You're probably gonna find some there too. There too. That's the problem with these imaginary zeros. You can stick them wherever the hell they want to be. And so when they do that, they're gonna form little rings around them because these things want to gather more things around them. Gather more things around them. So as you can see, these things like to gather rings around them because the rings keep getting smaller and smaller and then get bigger. and there's like the random places too, so it's really hard because these things don't connect very well. They're not equal spacings, so this is going to be extremely chaotic, and yet still have visual patterns forming because they're forming equal potentials here. These are equal potentials, where that is essentially the same information getting passed around at that point, and that's curvature equal potentials. All right. And so now we have all these curvature equipotential zones that are appearing at random places, and they have kind of this like halo-like structures. Okay, so now we have dark matter has allowed. Well, dark matter exists in this format, in this model, and it was emerged from just kind of the idea that, well, I don't know what happened here, but this is starting to emerge. Let's see if I can get this in here. Make it look a little bit better. Curvature equipotentials, and this is in fact dark matter. Okay, so um, I think I might have gotten through most of this page. I think I need to get through this page too. There's a lot of stuff we kind of got through here, but it's best if I go through here. Well, I wanted to derive some timestamps. So let's see. Let's say I had a pretty straight line, and for all intents and purposes, that line is pretty straight. And there's going to be real zeros along this line. 0 points, that. Um, so this is an interesting line. This is a timeline. Of course, we start from negative time, and then we tick this way. Um, we're going to designate this as sort of like, we'll call this sort of like our time being 0 seconds here. Because we're just going to start a little stopwatch, and then we're going to sort of let 1 second go by. Well, what's interesting is that during this entire second, and I guess we'll just call it second in here, so we're second. There it is. I don't know, whatever. Can I put 0? 0, scooch this over. There. Okay. This is where we kind of clicked it here. Um, well, the problem is that quantum info has to be funneled along this axis. And the way that it does this is it's going to basically rotate out little pieces and try to get to the next zero by hopping, essentially. It spits out this little particle because it had to rotate into this imaginary dimension. Follow this little line here. This is just imaginary stuff happening. Imaginary stuff happening here. Spits out these particles. We ask ourselves, what does this remind us of? What does this remind you of? If I drew a little red thing there and I drew, I don't know if I can draw this right, but let's see. Let's see if I can draw the freaking Pikachu. Oh my god, this is so horrible. Pikachu. Yo, I need a picture. Alright, that's so much better. Okay, check it out. So we got this crazy thing just like popping out like this. And he's just like, yeah! That's what this looks like. Hold on a second. Let me get this right. It's like that. With some paw prints. He's got this crazy tail. And, this is his feet. The feet are like down here. And he's just like super excited. Two crazy eyes. Uh, how are the ears to look right, man? Yo, this is the worst looking Pikachu I've ever seen in my life. But like, honestly, what am I supposed to say? Maybe it's another type of Pokemon. God, maybe we could rectify the situation if we just draw good cheeks, draw a happy mouth. No, that's even worse. God, that looks terrible. Oh my God, what are we gonna do? How do we make a good looking Pikachu? This is terrible. Oh my God, let's get some ears here. Is it starting to look almost like Pikachu, please? Ooh, there's gray tail here. Come on, come on. His feet are just like, I don't know, hard to draw. What about the arms? Where did the arms go? They literally disappeared. The arms disappeared. More like here, okay? Oh my god, it's almost starting to look like Pikachu. I think we need to get a red mouth. Maybe more like, less clown-like. Gosh, that looks so scary. Give him some more yellow, maybe? Poor thing. Almost. I almost got the Pikachu. Holy smokes. Just need to round out the body a little. Get a decent back, because there's no back. And the tail. Oh, come on. Come on. Come on. Come on. Come on. Oh my God. It's starting to form. It's starting to form the Pikachu. Look at it. Oh my God. Okay. So this is how particles straight up pop out of these freaking Pokeballs. I'm not kidding. Alright, this is one of the particles popping out. And I'd like to follow it down the line. Consider it like a photon or something. Okay, because it had to pop out at each of these little points. Okay, so here. And so every time it pops out of the Pokeball, at each one of these little zeros, and then it gets enclosed again. See, it pops out and then gets sucked into the next one. Pops out and then pulls into the next one. You see? And so that is how basically what we're doing is we're handing off the quantum information to the next Higgs. This is just like snippets of time. Like this is time moving forward. There's no way that we can avoid going down this line. But if we're trying to quantize the timeline, we have to imagine that these zeros that are along the line, we just follow the Riemann zeta function down the real line. Say it's a straight line because for all intents and purposes, on the very quantum level, this line is straight. So, you know, the curvature has no effect, right? Okay, sure. Like if you go really, really big, yeah, it'll have some effect. But let's not worry about that until later. I think we already sort of showed the effect of the curvature happening over there at the larger levels. But on the smaller levels, it's more like this. So we pop out with these little Pokeballs, and we go back into the Pokeball. You pop out of the Pokeball, and you go back into the Pokeball. Each time you pop out, you have a probability of showing up at any one of these little points in time. But let me just make sure that we could say that at each one of these things, a little Pikachu pops out. Every time, it just pops out here, he pops out again there, and he's just like pops out at every time down this line. We can measure the Pikachus, but we're essentially going to be taking a random, there's like a random snippet right here where it pops out. It's this kind of very random. So you might measure it, if you do happen to measure it, then you'd get timestamps essentially when you measure this stuff. See if I can get the right color going on here. Yeah, I mean, let's just say here you get a timestamp of T1. Here you get another timestamp T2, another timestamp T3, T4. As you get these timestamps in between this, notice how it's not always even. So here it was more to the right side, you know, so T6, here is really on that side, so T7. But there's a pretty high probability you're going to get right about in the middle. So if you measure it, pretty likely to get right in the middle. And we have T8. Alright, so yeah, it's not even. It's definitely all weird, like random. Um, but this allows us to get some timestamps here at what time these sort of particles popped out. And if we integrate from 0 to 1, well, we're gonna have to rigorously prove this, so let's get into all that. The idea here is that we can claim this 0, 1 right over here, simply equal to 0. Okay. Um, but we know it's gonna have an imaginary component because we're working with a spin 1. So we can call upon the imaginary. So what we can do now is we can say that we're going to take the 0, 1, then we're going to have to Fourier. So we're going to have to Fourier forward. And we're going to Fourier into uh, the voltage expectancy that is from the Higgs field. So the Higgs field essentially does this symmetry breaking, and this is the voltage that the expectancy value that we essentially pull out. So it's going to get one of these voltages. But when it does that, we have to Fourier again, this time backwards. So we reverse the Fourier, and now we're back to another zero. Okay, but this is the next zero down the line. So we have suddenly passed information from the first zero, and then we did a little symmetry breaking to pop out something, and then we had to basically Fourier back to the second zero here. And what happens is we can essentially solve this thing by saying, anti-Fourier of this, and then you get the next zero. And what does that really equal? Well, this thing has encoded some information and passed it along, right? What kind of info would we want it to pass along? Well, let's just see. So frequency at a particular Tn that we have a timestamp that we have found. See, at those timestamps, we can measure the frequency. Right there, you can measure the frequency at a timestamp. So the frequency at that particular timestamp, we're going to measure, and it's going to be Wn over 2 pi, omega n over 2 pi. This is corresponding to that particular timestamp. So we get a frequency. And with Fouriers, we can pass frequency values across. Because we know the frequency because we get a timestamp. And so frequency timestamps, frequency is 1 over time. So they're related. If we want to get the frequency in the next one, let's go to the next blip in time. Yeah, and I'm going to call these little things blips. This is a little blip. Each one of these things are blips. Alright? This is a little bit insane, but we just have to kind of roll with it. So each blip in time gives this possibly a way to change the frequency. So we can pass frequency information. This is the second one. We get the previous one. We change it a little bit. Okay, this helps us to sort of pass frequencies and change the frequency if we want to. It doesn't have to. This is one way that we can sort of pass some frequency information down the line. But there's more things we can pass down the line, so let's get a little bit better stuff. So let's take our phi here, a little thing. Let's take our 0. And we want to know sort of the effect of like the next 0. It's like at the timestamp, after the timestamp in a sense. The subscripts can get a little bit difficult. We're going across all possible frequency values here. And we're going to take frequency. So we integrate across all frequencies. Okay, yeah, this is kind of the idea. This is 0. Is it kind of more like this n plus 1? If you want to get the next thing. Okay, well, we're gonna have to look at that a little later. But what we get is this e, so negative I w t n equal to a matrix. So we can take this. How do we get this to be correct? I think it's supposed to be n. So essentially, near that, whichever one you want to do, but near that particular t-value, either this one or that one, whichever one you want to label this. But the idea is this is going to kind of give you information about the next 0 in line. If you have information about the frequency, then you can get this matrix. This is a little matrix, and we're multiplying it by the information that the previous 0 had. Hey, how's it going? I remember Mr. Apple. What's up, man? Some crazy stuff. So let's try to figure this out here. So we have our TX. So this is previous 0, previous 0, and this is the matrix here, which encodes info. And it basically encodes uh, all this stuff. Sphere force in the field generates a spherical field. Yeah, I definitely agree that the mass and size are going to affect the gravity. It's going to affect the curvature of these lines here. And the bigger that is, the sharper those curves are going to be. Is essentially what's going on. But let's see. So I got to get this notation correct because it's a little bit scary to look at here. So this is the next 0 right here. And then what we can do is we can essentially perform a little operation. I believe this is the Fourier operation here. Let me just double check what that notation means because the squiggly line on top has always gotten confused. What does the squiggly on top of the Fourier mean? I want to figure out what that means. The squiggly line on top of the Fourier. Oh, yeah, 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 yeah. Oh, this is a reverse Fourier right here. Well, no, that is the Fourier. Okay, yeah, yeah. So this is the Fourier. And then I believe that this whole thing is a reverse Fourier because we had to we had the Fourier in the first place, and then in order to get the information from the next zero, so this is the previous zero. It kind of looks like this. When it goes this way, we have to go this way. So this is like that, and because we took this previous zero and we Fouriered it, and so we get this particular thing, just this. But if we want to get this next zero, then we have to take this and Fourier and reverse Fourier that. And so now we get this. So from here, this is actually a reverse. So all of this stuff that we've done here, this is basically the reverse, which allows you to go this way. Whew. Okay, so this is how we can extract information, and then we get this little matrix over here. We can encode, we can put stuff in this matrix here at this previous point in time, and then things will Fourier forward in time, and we can extract that because we can just perform this little operation, and we can extract the information that was put into this matrix sometime in the future. So this allows us to pass quantum information down a timeline by Fourier transforming. Okay, and each one of these things that he pops out is on this side, on the left side, we encapsulate this thing, or we shoot it out with a Fourier. So here it is. This is the Fourier outward. Oh yeah, we have to zoom in on this a little bit, okay? Because this is kind of important. So we have our zero here, and our zero here, and a little space between them. When we can go out, it's about here, and we can pop out of the Pokeball. So here are the Pokeballs, and that Pokeball wants to pull it right back in. See, it's going to follow this line right here. Comes out of the Pokeball and then wants to go right back into the next Pokeball. And we found it at time here. This is some Tn that we found. In order to go upward this way, we have to Fourier. All right. In order to get the next step over here, we have to reverse Fourier. It's that simple. All we're doing is we're getting, starting with the zero, all of a sudden out here it pops out with a one. What? We had the Fourier from zero to one, from nothing to something. And we're going to prove how we can Fourier from zero to one a little later. Because there's the mathematical proof that we can actually it's going to be right here. We have to do this in order to be able to pop out ones out of nothings, ones from zeros. How on earth are we going to do that? Pop out with a one from a zero. We have to Fourier. So um, let's see. We can define a wave function, right? Xt, and that's supposed to be equal to, I believe, I don't know what this arrow means, but let's consider the Dirac function. Forget about this. Let's consider the Dirac delta function. x minus x naught. Is this supposed to be equal to 0 when basically anywhere that you have some kind of an x is not the origin? Or it's equal to infinity when x equals 0. Some other stuff, right? So basically, this is kind of how this function works. It's a little bit weird, but it's equal to 0 when you're at some x from negative infinity up to 0, but not 0, and then positive infinity. Okay, so everything except 0, and then at 0 it's just infinity. And so what this kind of allows you to do is it allows you to pop up with a new axis essentially. So you have everything is 0, and then all of a sudden there's like this infinity that pops up here. What does that remind you of? It kind of reminds you of going in one dimension, and then all of a sudden there's another dimension here. Oh, and it's at the 0 point. Well, isn't that an axis? So, essentially, as gravity suffer as the scale reduces in size. Yeah, so essentially, gravity is essentially going to be negligible by the time we get to a single one of these little things. Then that's why we have like this particle in a box, and it's just like, oh, if you calculate it, you get exact, percentages here. Like it's pretty much exact. There's no curvature being here because this is flat for all intents and purposes. As you start to get longer lines, notice how this line has a little bit of curvature. So if you did a really long integral across a large portion of space-time, now you're going to start getting more curved lines and stuff. So it becomes more important to, and then the quantum effects just go away because now quantum doesn't have anything. So yeah, there's that kind of annoying thing where it's like, well, I don't know. But yeah, gravity definitely goes away when you're up really close. So we're zooming into the up close here, and we're trying to ask ourselves, how the hell does it function? Well, if all of a sudden we're going along these zeros, and then we pop up with this infinity right here, it kind of reminds me as if we're kind of going along this axis right here, and all of a sudden there's just like an axis that pops out of here. And so we've sort of defined that here we're only moving in one direction, x direction. But then over here, we just pop up with an axis. So essentially, this allows you to spawn axes. Decoherence. Yeah, for sure. Decoherence is definitely um, one of the reasons why we have this crazy. I wouldn't necessarily call this from decoherence, but to realize that the reason why these dark matter halos tend to appear seems to be because, like, the Riemann axis itself, if you look at the zeros on the Riemann axis, the zeros get smaller and smaller in spacing as you go out, as you can see here. So if you were to try to curl those around, it's not even like the other type of gravity right here. Like the real zeros, they're not gonna be as chaotic. They're much more formed, and they're gonna make little planets. You can see these are equipotentials where the planets would form around this. In fact, let me go ahead and add that in because this is Earth right here. Or no, that I guess that would be the sun. But sure. So here's the sun. Okay, and then I don't know. Here's planet Earth. Here's nothing. But you would have these kind of showing up at different equal potentials where it's just like, okay, that's the perfect spot to have the next planet would be right around there, and so it can follow this kind of idea here. Um, yeah, I don't know. So let's just see what happens with the Fourier transform over here. I want to make sure to get this Fourier going properly. Okay, this thing here gives us the frame rate of reality. I was trying to calculate this Fourier and trying to calculate how many blips per second. But if we consider that Planck length is equal to about 5.4 e to the negative 44 seconds. Um, and we let 1 second go by in our world from 0 to 1. Yeah, exactly. Uh, they got to be good angles. If the angles are starting to become uneven, then it's going to be hard to line things up. So if the angles were even. That's why gravity works much more like uh, the real angles are pretty even on the real axes, but on the imaginary ones, like the angles will be changed based off of how far you are. So like you're getting these very strange halos around. I don't have a picture of dark matter, but if you look it up, this is exactly what it looks like. So it's kind of crazy how the imaginary zeros and the Riemann zeta function, they model dark matter pretty well. But the idea here is if we have 1 second pass and we have, say, each one of these little blips between the zeros here, um, this is the TPs would be more like every zero. That's a TP from here to there. Yeah, okay. And then so basically, if you measure from this one to that one, it's going to be about that much seconds. You could timestamp it by finding it there, and then the next time you can maybe try to measure it if you can get it in time, but you're probably not going to. But this implies that in 1 second, we would find about 1.9 e to the 43 blips per second. So that's how many times these particles pop out of their Pokeballs and essentially interact with the zeros. The neutrinos definitely exist, the real ones at least. I don't know if dark matter neutrinos exist, but the real neutrinos have a spin of I think 1/2, and they should be like an antineutrino will spawn from like some other stuff. But I don't know if they're dark neutrinos. I don't know if they're dark neutrinos. Um, but it may be. Who knows? Frame rate reality is going to be essentially this is the frame rate. We have a frame rate of 2e to the 43. That frame rate is so fast. It is actually ridiculous. This is indeed the frame rate of reality right here. For every 1 second, we have about 2e to the 43 frames. And that's the frame rate. So you know, our eyes are essentially the best cameras we have. Well, unless we have bad eyes. Yes, that's kind of a bummer. All right, what else do we need to do here? So we've shown the blips. We've done a little Fourier, kind of. We need to get more details out of the Fourier because this Fourier is critical to be able to complete this process. Uh, so if you wanted to get a final value, that's some timestamp. Let's get a final zero going here. If you get to the final zero, it should be able to get a lot of information pulled out because it should have received all the information that came down the path. And if it doesn't get all the information, that would be decoherence. But if it managed to receive all of the information, then here's what would happen. So we get mn, mn minus 1, and then now we can keep going, dot, 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 until we get to the very first m1 that we had multiplied by the very first 0 that was near t1. It's t1, and this is the very first 0, 0, 1. It's near 0, 1, either left or the right, whatever way you want to do. We found this particular timestamp, and it had some information encoded in it. Then we pass that information across a series of matrices, and then these are just multiplied by each other. So we're doing that times that, that times that. There's a whole bunch of them in between, and that times that, and then we've reached the final matrix. We just multiply these matrices. This is, I think, this is a process in linear algebra, and this is essentially doing several linear transformations of. This is literally what we're doing here. Is we're doing linear transformations. And this is how we're able to pass the quantum info, which gets encoded into these matrices. This is the quantum info right here. Basically, quantum info is being passed along the zeros. And they're linear transformations. This is the linear transformations, which means if we return to our unification model here, and ask ourselves, what are we really doing here with these transformations? What does linear transformations forward in time mean? It means that we have straight axes that we're following down and we're doing okay. Time's going straight. But what happens if we have curvature in the lines? If we have curvature in the lines, we're no longer doing like exactly straight transformations. So on the grand scheme of things, that affects the curvature. On the smaller scale, that curvature is negligible. So that is very interesting. Curving the lines of the Riemann strip to disprove the Riemann hypothesis is now leading to a model that basically works perfectly to represent the universe. Um, Interesting. Keep in mind that in order to Fourier transform between this little thing here, we had to pull out a random timestamp. So we had to integrate from negative time here of a value of negative infinity and a positive t over here with a value of infinity. And we had to extract a time value here. How did we do that? Uh, let's figure that out in just a second. We'll come back to that because it's really important. But over here, let's note that a photon has zero mass. And so therefore, what does the Higgs really tell you? It has curvature information. This photon can go through this forever. It can be slapped a bunch of times, and they won't cause any kind of slowing down. Other particles are going to smack against this stuff and essentially slow down because they have mass. So other part, this is essentially like a little, I don't know, it's like this little this little thing that's sort of sticking out, and you have to like run by it. It's those little spinny things that like you have to run by it, but yeah, it's like slowing down your progress, so it's like causing you to slow down. So other particles, massive particles. See if I can get some space going here. A little bit of space. A little bit of space. Oh my gosh. Let's get a little bit of space right here. And let's remember that massive particles will will slow down essentially due to the smacking against all these timestamps in a sense. So we could see the photon would be unaffected by spinning out and spinning back in. Massive particles would require energy to do that and essentially donate their energy to the manifestation process and end up draining that energy as they manifest at every point in this model. I need to find the dark energy. But the question is, did the stream kind of cut itself real quick? Don't know what happened there. I'll double check. My computer isn't all that great. Okay, I think it's okay. Uh, where were we? So we have void. This here is a void. This is a void. And I think that's it for this page. I'm already going through some of this stuff here. Let's take a look at what it means. Integrate from negative infinity to infinity of the Dirac function, which for if you were looking at it from far away, you'd be pretty convinced that this was zero because it's zero everywhere except for one point out of infinity, double infinity, both ways. And yet there's one little point where it's infinity. It's just that one little point where it's infinity. Everywhere else it's zero. So, you know, if you're looking at the Dirac function, it's zero. All right. So you take an integral of this, and here's the magic. The integral from negative infinity to infinity of zero is one. Yeah. So this is a formal statement, mathematically formal statement that says, and look, who invented the rules of math? Mathematicians, right? So, there's this rule that says that infinity times zero is undefined. But that is true if you're just using normal numbers. But if you use this particular arrangement of numbers, then in fact, infinity times zero, infinity integrated over this particular zero function where it's at one point, there's one infinity, that exactly does equal one. So we have basically said here that in this case, this is equal to one. Yeah. Hmm. So, okay, this allows us to be able to Fourier transform from zeros to ones. That is how we're doing this whole process of going from 0 to 1, 1 to 0, 0 to 1. And I believe, fields are contracted as you go back in time, or stretch further as you go forward. Yeah, yeah, the fields exactly would be stretched further and backwards for sure. So what is true for one state and the fields is not true for another? Is this issue with contract restrictions? Yeah, exactly. Depending on which field is stretched one way and what field stretched another way, like the imaginary field can do all sorts of cool things because it's got this spinning stuff, so it does all this weirdo stuff, but it's all linked through the real zeros, the coordinates here. I think I drew the coordinates here, and you can see how this is a real world right here. It's pretty simple. It's just got a couple of real zeros in it. These things can curl around and interact and stuff. But look at all these other fields that there exists out there with these imaginary components, right? These things fold up and curve around each other and stuff, but they're all linked through the alpha. That's the curvature. So dark matter affects the real axis only through curvature information. That's the Higgs. It's understanding, a little bit of what's going on out there. It feels uh this tug, but it's not really real there. So, just got all this stuff happening. Yeah, I don't know. This is weird, man. This is like this is like the Da Vinci Code or some shit, man. It's like freaking this is like aliens, ancient aliens, dog. Neutrinos? I think neutrinos do exist, unless there was a problem. Neutrinos don't exist? Is that what happened? Oh, yeah, no, no, no. So I think the sterile neutrinos, I believe. Or wait, are they saying real neutrinos? Why neutrinos came to exist? I haven't heard of this, so I'm not 100% sure of this. I haven't heard that neutrinos don't exist anymore. Like we found evidence of that because I know that recently we found sterile neutrinos don't probably exist because of, well, we put restrictions on the size of the sterile neutrino. That's the dark matter one where like we can't find it because uh it's not that particular value, so we don't think it exists during in that range. But I haven't I do see that there are some posts that say that neutrinos might not exist, so I have to do some more research on that and see what kind of info we have about these neutrinos. Haven't really looked into that too much. But let's see if we can define the wave function that would be a helpful wave function to use. Didn't we already have the grand wave function? I don't know, I think we've pretty much gone forward with this particular page is pretty much complete. Um, Although one last thing that we might want to consider is that in this situation here, there's when we can Fourier between time and frequency, we can Fourier between position and momentum. So those are some ways that we can Fourier transform. Obviously, there's different ways, and you know, the ideal idea would be to be able to Fourier between these two as well. But we'll see if there's a possibility to do that in another way. This is quantum coding, so I'm not going to do the quantum coding in this particular video. It'll be for another video. But I do have this important Fourier to complete. So this is probably the most important part as to being able to rigorously prove this Fourier. If we could do this, then that would be great. Here is the initial wave function, aligned specifically to that zero. We're going to give it a state of zero. Um, what we can do on the side over here is that we can get this energy of an electron value and divided by h, and that will give us a frequency. And if we wanted to, we could use an external source, for example, to induce this, although it will just happen naturally if you wait a split second. So no biggie. But like, yeah, we could probably induce this by adjusting the energy and doing a little change of the potential. And you might be able to manually adjust this to spawn an electron. But the idea is here is that now what we're going to do is we're going to Fourier here, which is going to spawn particle. And so we have to take our thing here, and now we can see the timestamp now because now it's popped out. So now we give it a timestamp down here. This particular wave function is equal to e to the I wt. My hand starts hurting like crazy. So I start writing a lot. And I believe that this is actually T1 and also W1 as well. But I'll give that a green because this is kind of like the frequency. You can imagine that being the spin, even though it's probably not, but just imagine that as being the spin real quick. Let's understand what's happening here. So this is our W. This is the information that gets passed out or gets sort of uh, attached to this timestamp. W1 gets attached to timestamp T1 through the Fourier transform. And this is a state 1. In order to get this, we had to encode the info. How do we do that? Over here, this is how we did the transform. So integrated from negative infinity to infinity e across all w values. So we don't know what the value is yet. And and then we have remember that we had to previously encode we have to Fourier twice, so it's really important that we keep track of how many times which Fourier we're on. So this way we have to Fourier this stuff has to get Fouriered into here. That makes sense? I don't think so. I think it's fine. that cross the W's though, right? Is this right? VW. So essentially, at one of those timestamps, you'll be able to blip out frequency. You have to integrate the frequencies from negative infinity to infinity to be able to get the frequency. But 0, 1. This is kind of a really difficult integrals or a very difficult process. So it's very difficult to understand what I'm doing here. We have this initial, which is a 0. We're going to Fourier it to become a 1, and then we reverse the Fourier. So this spawns, and then this gets recalled back into the Pokeball. So now we sort of have this wave function that came from T1, and this will be the second 0, but it was affected by T1. And this is going to be equal to uh, almost the same thing. This goes back to 0. So kind of like this one. Got some nice little 0 there. So I put this one here. Um, Here we have a T minus T1. So I think it's kind of maybe waiting for the next timestamp or something. This was the spawn time right here. It has information about the initial frequency, and we somehow pass that information to this second 0 here. And hopefully this Fourier is correct. I have to just double check this later. Um, but in order to get this one, we had to reverse this Fourier, meaning we had to take this now and integrate that. Right. And it gives us this ability to take Keep in mind here again we are now there's a way to get this math right, but it's a little bit tricky. See if I can go back over this. I'm not like 100% familiar the uh with Fourier transforms, so it's hard for me to identify where the mistake might be if there's a we start with a completely blank slate here, and then we're looking to encode that info into this. Pass the time value along. Seems like I might be losing this W information because my instinct says that I'm going to need to delete this W here, which may be okay. I think what we're doing is we're passing the T value down this line or something. I'm not exactly sure. I'm gonna have to sort of double check what we're doing here. But the goal was essentially to show how we can Fourier between the 0 to the 1, then back to 0, and with that, carry some information. In this case, I think we managed to carry the T1 down the line. Timestamp information, which would be interesting, but I'm not too sure what else. I think we were trying to encode some frequency info. So I think we may have encoded the wrong info. But regardless, this is an interesting example, and that was that. Let's see. Let's see if I just want to write down the vacuum to vacuum transition amplitude. So that's done. Here's the vacuum to vacuum transition amplitude. Vacuum to vacuum transition amplitude. Whatever this means. It is right here. And it looks like 0 e to the I integral d to the fourth x Lagrangian using J. I'm gonna have to do a little research on what the hell this even means. And then we head back to a 0. I wanted to jot these things down because just have them written on my paper. I was doing some research and yeah, yeah. So it's kind of I mean, the math is leading towards some interesting ideas here, but I don't know if I'm getting the exact notation correct. I'm sure I'm making some notational errors here, not passing the right information down. But someone who really knows his math better could potentially get this right. All right. Uh, yeah. All right, so finally diving back in transition to why are we using this Lagrangian? I think the Lagrangian we were trying to force we were trying to force the Lagrangian into certain modes of excitations. The Lagrangian being 1/2 d mu phi d mu this direction phi, and this here is essentially a double derivative. You can imagine this is like a derivative of that thing squared. We'll go into that a little bit later, but then we have the minus 1/2 m squared phi squared. This is the potential, the Higgs potential field here. And then if we wanted to, we could potentially use an external source to sort of jolt or, this thing into some oscillational modes and sort of potentially prod the zeros, the zero field, prod the O field. So we could prod the O field and induce excitations with an external field here and basically potentially create an electron or some matter. Of course, you'd have to do one antimatter and one regular matter, otherwise you'd have some problems, but that's kind of what we're doing here. We'll describe how particle annihilation and creation happens when we deal with particle annihilation and creation is essentially coming up soon, I guess. We have to show the grand Lagrangian that puts all the theories into one. I think we've basically finished this stuff here. Is that right? How many pages do we have here? Oh no, this page is important. This is the next page. This is about quantum coding here. And that's the final page. And then here is kind of what we just did. The Casimir effect. Are we going to deal with the Casimir effect? Oh, do I put that over here? Okay, well, let me just mention that uh, some other time, we essentially warped stuff into existence, yeah? It seems a little bit crazy that we would be warping stuff into existence. Nothing. Alright? It seems a little bit crazy. Where's the wormhole where we see everything warping into existence? The wormhole. Gotta go find that wormhole. Quantum gravity's here. Unification is here. Uh-oh, we have two things open. Same time, I have to close this one. Keep this one. And what do we do? Go to statistics? Is this where it is? No, I don't think so. I think, uh, yeah, exactly. The Casimir effect. You know about the Casimir effect. Um, Basically, there's like electrons and stuff, I believe, that form in between conducting plates. Well, where's the spawning process? I drew it somewhere, but I can't find the drawing. I don't know. It's a little bit weird. I think maybe I drew it in the standard model. It's probably where it is. Yeah, there it is. Okay, here we go. Boom. So right here, we've warped something into existence. And that seems to be a little bit scary. And it would totally make sense that one would be inclined to not believe. I don't believe that things are warping into existence between here and there. That seems impossible. But let me just double research what the Casimir effect is. Yeah, okay. So the Casimir effect is essentially where we've observed this phenomenon happening between uh two charged plates. Um yeah, so essentially the quantum CPO, the O fields are spawning shit into reality. And this is called the Casimir effect. On a sort of a smaller, more like, oh, we can see that happening. It's kind of like a more of a macro effect because this is with the electromagnetic fields and we have some charged conductors on either sides. They're very close together, of course. So now how can I do this? Charge on that side, charge on that side. It's usually going to be positive, negative, I believe. Attractive force. Um, Essentially, there's some fluctuations in between here, and little particles pop in and out of existence. Little virtual particles. So this is the Casimir effect. And yeah, there's a little bit more complicated explanations for this. So let's see if we can write down this equation here. Let me use the energy equation. So the energy associated with this stuff is like pi squared h bar c divided by 240 a to the fourth. And this is essentially the Casimir effect, the energy that is, I think this spawns one of those particles or something. Alright. Yeah, this is crazy. So we can actually see that this model, this theory that I have, that like, the quantum fields are spawning shit in the middle of reality, like, That's actually not too far-fetched, man. Like, we see the proof right here in the Casimir effect, man. What is happening? The thing is that the distances between these two zeros are so goddamn small that okay, yeah, these two plates are charged that far apart. But if you get even closer together, now all of a sudden, you got some real energy because the energy on the bottom is yeah, yeah, exactly. So, you know, yeah, so it's not that these things are kind of like subtly observed. They're not like fully materializing in our real world because it's all imaginary stuff, imaginary interactions, which is very difficult to get the imaginary interactions to work in the real world. But I think we finished this page, and then I think I'm almost done with what I sort of wanted to cover today, because there's this, which we basically got through. The other side is basically done. We had a very small amount of stuff to do here, but this is more about coding the quantum computer. So we'll wait for the coding the quantum computer next time. And then there's all that stuff. And then there's this stuff is like really, really crazy, so I'm not gonna go through that. Yeah, we're essentially almost done. The next piece is sort of going to be to go through the entire like standard model, Lagrangian and covariant derivatives and figure out how all this stuff works. But I think for now we've covered quite a bit of ground and have set up a little model, the model of the zeros that will really help us to understand how this universe functions. There it is, and the Fourier transforms between the zeros and the ones. And the coding quantum informations that can pass through the line of zeros and end up at the final zero. Man, this right here is so crazy. Like, this was sort of the revelation that sort of led me to think, well, maybe there's a way if we were able to pass quantum info to the next moment in time and we follow the timeline down. Well, one way that would work is that if each point along the timeline you had a point where you could sort of spiral out from and encode some quantum info, imaginary quantum info. We need an imaginary dimension popping out at each one of these zero points. Let's connect the zeros. So this is what we get out of that. I don't know, man. So this is some messed up stuff. Y'all have an awesome night. I'm just gonna go ahead and try to get some sleep today. Have fun.